So today we're going to start Unit 6, Lecture 2, and for this lecture we're only focusing on vitamin A. And basically I have vitamin A off by itself because it really doesn't fit into many of the other categories. And it's involved in many things, but the majority of us only think of the eye when we think of vitamin A, but it's actually involved all throughout the body. So it's hard to put it with the other vitamins. So vitamin A was the first fat-soluble vitamin that was identified, and it was identified by different groups between 1913 and 1915. And since it was the first vitamin that was officially identified, that's why they referred to it as vitamin A. And originally it was discovered by the University of Wisconsin, and the University of Wisconsin in Madison is actually the forefront of all the vitamin research, especially in the early 1900s. It's the university where the majority of all the vitamins were discovered. And it was in 1929 that it was actually discovered that carotene, which is a carotenoid, can be transformed into vitamin A. So most of our vitamin A, they are referred to as retinoids. Carotene is one of our carotenoids, and so that was discovered. And this is the whole reason why you were told when you were younger that you needed to eat your carrots, because they have lots of beta carotene in them, and that's good for your eyes. We have different active compounds that are all referred to that make up our retinoids. So our main ones are retinol. Our retinol is an alcohol form. Our retinal is our aldehyde. And then our retinoic acid obviously is our carboxylic acid. So here we have our different forms. You could see our retinol, our alcohol form. We have this hydroxyl group. And if you look at this vitamin A, we have our ring structure at the end, and then we have this long chain, and if you could see all these double bonds on the long chain. So because of all these double bonds, this is making vitamin A the least stable because of all these double bonds. So out of all the vitamins, it is the least stable. And it is very susceptible to heat, to UV light, and pH. And actually, if you ever end up working with vitamin A or any of the carotenoids, really, you have to do it under an amber light or actually work in the dark with it and have all your glass vials need to be amber glass because it is so labile and can be broken down really quickly. And then we have our retinal here. We have our aldehyde right there. So this little dot, that's our carbon. It's kind of hard to see in there. And then we have our retinoic acid, where we have our double bond oxygen and our hydroxyl group at the end. Now our carotenoids are provitamin, vitamin A, our carotenoids that have vitamin A activity. You can see here our beta carotene, for instance, it is basically two retinol molecules conjugated together. So they are basically a mere flipped version of each other. So in theory, one beta carotene can yield two molecules of vitamin A, but that actually ends up not being true because we have to, when we break our beta carotene up to form our retinol, we actually end up losing one of these components. And out of the nearly 500 carotenoids that we know of and have identified, only 50 of them, or 10%, so we have 10% of all of our carotenoids have some vitamin A activity. So not all of our carotenoids can be used to synthesize vitamin A. So just as we had the international units to normalize the different types of vitamin E that we talked about previously, we have a similar situation with vitamin A. So vitamin A, we have different types of retinoids and we have different types of carotenoids that we need to normalize because they have different activity levels. So for vitamin A, we utilize international units just like we used with vitamin E. However, you'll notice that the values are not equivalent as they to vitamin E. So here we have one international unit of vitamin A, which is, this is what your RDA is going to have. Your RDA is going to have, if you look on the back of a label, it's going to give you the international units of vitamin A that you need. So our all-trans retinol, so this is our alcohol, because we have the OL, if you remember your naming of your alcohols from organic chemistry. So this is the most potent out of all the retinoids, and this is what we set our standard to. So we have 0.134 micrograms of all trans retinol equals 1 international unit. Now, very rarely do we have naturally within our diet retinol. It's usually conjugated to some sort of fatty acid. So here, if we conjugate it to an acetate, which is a 2-carbon fatty acid, we're going to change the international unit to 0.344. Now, the most common of all the retinoids that you're going to be consuming is actually retinol palmitate. So if you conjugate it to palmitic acid, which is 16 carbons long, this is the most common. And it takes 0.55 micrograms of all-trans retinol palmitate. And if you notice that it says all trans, this is actually referring back to that long chain off of the ring of the vitamin A. And if you look and notice back at that structure, that we have all those double bonds, and all those double bonds are actually in a trans configuration. So that's what this is referring to, is that chain of those double bonds. So we also have retinol equivalents. So this is what we're utilizing to compare the provitamin A activity of the carotenoids. So an RE is going to equal 1 microgram of all trans retinol. If we want to convert our beta carotene, so our all trans beta carotene is going to be 6 micrograms, is going to be equal to 1 RE. So you can see that it actually is not as potent. It does not have as much vitamin A activity as retinol does. And beta carotene is by far has the greatest activity of all the provitamin carotenoids, because here you could see any other provitamin carotenoid is going to end up having a RE of 12 micrograms. So how do we digest vitamin A? So as I mentioned before, it's in our food as retinol esters. So it's esterified to fatty acids, and the most common one here being palmitic acid, which is 16 carbons long. And vitamin A, just as, since it is a fat-soluble vitamin, so if you Remember that from the last lecture. So it is fat soluble. So we need it to be within our micelles. So we disperse it into the micelles, and once we have our mixed micelles that are able to move into the unstirred water layer, we're then able to have passive absorption occur. Now, just as with many of our sterols that we have where we need to cleave that fatty acid off, we have to do the same thing. So we need to break those ester bonds. So we're going to have one retinol and one palmitate. And this is the most common non-esterified fatty acid that is going to be conjugated to retinol. And also within the intestine, we have the vast majority of our provitamin A carotenoids are at this point in time converted to retinol within the intestine before they are absorbed by the enterocyte. Now, this obviously is not all of them because this is what we are utilizing for much of the pigmentation. Our carotenoids are utilized for pigmentation all throughout. So that's what gives flamingos their pink color. That's what's giving chickens their yellow color on their skin. So there are many components of the carotenoids that can be absorbed. But if we're going to be utilizing those carotenoids for our vitamin A, we are utilizing those and converting them to vitamin A within the intestine. So how is vitamin A absorbed? So once we get it digested and we have our retinol and our fatty acid, our palmitic acid is able to go through the fatty acid transport protein 4, where our retinol, we need to utilize cellular retinol binding protein 2. So this is within the enterocyte, and it's going to be binding the vitamin A, and this is to prevent any detergents, just like we're going to be having with our fatty acid binding protein to prevent any detergents. We're also trying to prevent any detergents forming with our vitamin A, and it's also protecting our vitamin A from any oxidation that's going to occur with all those double bonds that are susceptible. So we utilize the CRBP2, cellular retinol binding protein 2, when we have deficient to adequate amounts within our diet. So if you are deficient, you're going to have higher levels of CRBP2 that you are making, so you will be more efficient at absorbing the small amount of vitamin A that is within your diet. However, once you have high levels, so if we start getting into taking supplemental vitamin A, for instance, anything greater than adequate amounts, we're going to be able to have our retinol pass by passive diffusion. So it's passively going to pass through our intestinal, our enterocyte, cell membrane, and go into the cell. So this is where we can get toxic amounts. And some of the reasons why it's bad is that vitamin A can have a detergent effect. In addition, the way vitamin A functions, it actually is involved in gene transcription. So we're going to have a lot of changes within what the cell transcribes. Quickly, as soon as it is brought into the cell by the cellular retinol binding protein 2, we want to re-esterify it to retinol palmitate within the enterocyte, and that we're using LRAT, so lecithin retinol acyl transferase, also known as LRAT. So that happens within the enterocyte, just like how we want to bring our fatty acids back to being a triglyceride. And then once we have retinol palmitate reformed, we package it into the chylomicrons, and just along with our triglycerides, and it's transported into the lymphatics. If we're talking about chickens, it's going to go into the blood. It can be bound to protein and transported in the blood, so that's mainly going to be binding to the albumin. This is mainly going to occur at very high levels within the diet. So that's not going to be too common to have, but if you have high levels of vitamin A that you're consuming, you take a lot of supplements, it can be transported into the blood, and that's another place in which it can cause issues. So here we have a schematic of what's happening for our digestion and absorption. So here you could see we have our retinol esters come in. Our lipases are going to be breaking them down, and this includes just pancreatic lipase. You have the lipase esterase and some of the phospholipases so all of them are involved. So once we have our lipases, they're going to be breaking it down into our retinol. So here we have our retinol go into the cell. Some of our carotenoids can come in and they are converted to retinol. Also, so we have our retinol binds our cellular retinol binding protein 2. And then we use LRET to convert it back to our retinol esters. It goes in through chylomicrons, goes all throughout our body, comes back to the liver. So hepatocyte means liver. Hepatocyte is a liver cell. Now, within the hepatocytes, we have the retinol esters are then broken down to retinol, and we have our retinol binds, cellular retinol binding protein 1. And if we need to bring our vitamin A or retinol to the rest of our tissue, we're going to bind it to retinol binding protein. So we have a cellular retinol binding protein, and then we have an extracellular retinol binding protein, which is just referred to as RBP. And so it binds RBP, and it can then be transported throughout the blood. So notice that there is no lipoprotein when we are bringing our vitamin A throughout the blood. So the main way is retinol binding protein is how we're transferring our vitamin A throughout. So if we have adequate levels of vitamin A and we want to store some away for the rainy day, we have some cells within our liver called the stellate cells over here. So this is mainly, they store vitamin A. And this is the whole reason why liver is a great source of vitamin A. And I believe the polar bear liver actually has toxic levels of vitamin A. So if you were to consume a lot of polar bear liver, which probably is not anything likely that any of you will do, but eat it in moderation so you don't get vitamin A toxicity. So we're storing our vitamin A within the stellate cells. So here you can see we use the LRAT again, and we're converting our retinol back to our retinol esters, and we're storing that within our stellate cells. And then when we need to access that vitamin A, we're going to be releasing those retinol esters back to the hepatocytes, and we're going to be breaking it down to retinol and then have that go bind the retinol binding protein and go throughout the cells. Now, you may have noticed that all throughout this lecture so far, I've mainly just been referring to retinol, and I haven't said much about retinoic acid or retinol. So we have retinol palmitate or our retinol esters. So this is coming from our food, and this is also how we store. our vitamin A. So you can see here these double arrows on this line, so this is reversible. So this reaction is reversible. We can add a palmitate and we can take it off to where we have retinol palmitate. In addition, you can see here going from our retinol to our retinal or retinaldehyde that this is also reversible. So we can interchangeably go between retinol and retinol back and forth. So retinal's main function, and we'll get to this in a little bit, is mainly through the eye. So that's the main way in which we're going to be utilizing retinal, and that is also a way we convert retinol to retinal and then to retinoic acid within the cells that need to use it. And you can see here that our retinoic acid cannot be converted to retinal or retinol. So we have this one-way arrow over here. So this is irreversible. So this is one of the interesting things where was actually discovered utilizing chicken and chicken embryos. So they made these hens vitamin A deficient. So they were deficient. However, they were given a diet that had high levels of retinoic acid. So they did not show the typical clinical signs of vitamin A deficiency, and then had these hens lay eggs, and they were fertile eggs, and they incubated the eggs, and they utilized that to determine, can the retinoic acid within the egg meet the needs of the chick? And it was that those chicks were able to hatch just fine, had no problems, but they ended up being blind because they were not able to convert retinoic acid back to retinal, and it's retinal that we utilize for vision. So those chickens were blind because we could not convert it back. So we actually utilized the chicken to help determine the activity of these different conversions. Here you could also see beta carotene, really any of our provitamin A carotenoids, they are also irreversible. You could see that here. Once we break down beta carotene to retinal or retinol, it is irreversible, and we cannot convert it back to beta carotene. So some of the functions that we have for vitamin A, our retinal, as I mentioned, is needed for vision. Our retinol is needed for reproduction. So to have a viable fetus, it needs to have retinol. Retinoic acid, interestingly, retinoic acid is actually the active form of vitamin A, and this is the main way in which vitamin A is actually working through. So as I mentioned before, we always think vitamin A and vision, and we need to eat our carrots to help our vision. But there's all these other components and functions that vitamin A is involved in, and it's all through the action of retinoic acid. So how is that working? What is retinoic acid doing? Well, it's involved in cell differentiation. It's involved in epithelial integrity. So it is actually working through gene transcription. So it's involved in gene transcription, so it binds a nuclear hormone receptor, RXR, RAR, and then that's in charge of transcribing genes. And one of the main proteins it's involved in are the various keratin proteins. And these keratin proteins are actually what's determining what type of epithelial cell that you have. So that's how it's altering epithelial integrity. So if you are deficient in vitamin A, instead of your intestinal cells being columnar, they're going to turn squamous, similar to your skin, and therefore you're going to have more of a leaky gut. Where if you have high levels of vitamin A or toxic levels of vitamin A, you're going to get a lot of cell proliferation and other epithelial integrity things are going to occur. Just as it's involved in gene transcription for keratin, that's also how it's involved in growth. It's controlling so many things within the cells, controlling cell cycle, etc. So that's how it's involved in growth. In immunity, it's been heavily studied related to immune function, and it's actually shown individuals that are vitamin A deficient, which in developing countries there is a incredible amount of deficient individuals with vitamin A, and those individuals are more prone to higher rates of morbidity and mortality due to measles, and it usually ends up having to do with a T cell response is most classically. So they say that if you're deficient, you have more of a Th1 response versus a Th2. You don't have to know that at all, but it's kind of fun. A lot of papers on how vitamin A affects the immune function. And Bill and Melinda Gates is currently funding a lot of research looking at this. The World Health Organization is funding many projects trying to decrease the morbidity and mortality, especially in young children with vitamin A deficiency. Our carotenoids, our keratin actually has antioxidant function, so it can spare our vitamin E and selenium and our ascorbic acid. However, once our carotenoids are used as an antioxidant, they cannot be regenerated like vitamin E and ascorbic acid can. So once these are used and oxidized, your body just gets rid of them. So here we have our description of how vitamin A is involved in vision. So here our retinol ends up coming in to the cells within the eye, and we have it first as retinol, and we need it to be first 11-cis retinol. So you can see we have some changes that occur. So we're changing from our retinol palmitate to 11-cis retinol, and then that's able to bind the protein opsin, and when we have that, we have the formation of 11-cis retinal. So we now have the formation of our aldehyde. And this happens in both the rods and the cones, so it's important for both to see color and to just see black and white for night vision. So here we have our 11-cis retinal. We have our photon light hit it, and then we have a conformational change going from 11-cis to now we have an all-trans retinal formed. And when we do that, we release opsin, and that is the release of the opsin is what's causing an electric impulse to be transmitted down the optic nerve. So the conversion, the light hitting 11-cis retinal causes a conformational change. All trans retinal, we're releasing the opsin, and that causes the electrical impulse sending signal through our optic nerve. And then we form our all trans retinol, and then the cycle just keeps on going back around, and we'll convert our all trans retinol back to 11-cis retinol. And as I mentioned, it's happening in both the rods and the cones within the eye. So that's how vitamin A works with vision. So how does it work for everything else? How is its function through retinoic acid working? So here we have all of our other cells, and this happens in every cell. We're utilizing vitamin A. So it's not just the eye. We have our retinol binding protein bound to our retinol that ends up coming into the cell through STRA6. And then we have our retinol comes into our cell. So this is our circle here is our retinol, and then we convert it to retinal. And once it's retinal, the aldehyde form, we then convert it to retinoic acid using retinaldehyde dehydrogenase 2, and we're converting it to retinoic acid. And within the cell, it binds cellular retinoic acid binding protein 2 and or FABP5, and it's able to then enter the nucleus. So once it's within the nucleus, it's able to bind these nuclear hormone receptors. So we have RAR and RXR. So RAR is retinoic acid receptor. And then RXR is retinoid X receptor. And so once we have our retinoic acid within the nucleus, and you'll notice that these are dimers, meaning that we need two of them. So we can have RXR bind various other nuclear hormone receptors, including PPAR, vitamin D receptor, so many various different things, and FXR, etc. RAR can only bind RXR, or it can homodimerize, where we can have it bind another RAR. And then these are able to transcribe the genes. So that's how this is actually working, and that's how we're controlling so many things with our vitamin A. As I mentioned before, it's utilizing our retinoic acid and the nuclear hormone receptors, RXR and RAR, in which we're controlling the epithelial integrity. So without vitamin A, our normal mucous membranes and cells are impaired. So usually you're going to have your skin is going to be more flaky, etc. And then we'll also have our cells within our epithelium. They'll become squamous as opposed to being nice columnar cells. And this is all through regulating the keratin protein expression within the cells. So when we're deficient in vitamin A in humans, we're going to have various diseases. Most commonly, and one of the first symptoms is actually going to be night blindness. And so this is due to a lack of retinal. So we're not able to have our aldehyde within the eye. So if we don't have our retinal within the eye, our protons are going to be hitting our eyes, and we're not going to have the signal of the opsin when it's released from the retinal. So basically you end up having night blindness, and it's mainly during at night where you actually need a lot more of the impulse, the electrical impulse, to be able to see. One of the more serious diseases is exophthalmia. So this is the drying of the conjunctive tissue within the eye. So basically, first, our cornea becomes very hard, so you have exorosis, and then it progresses and it becomes very soft, so you get keratomalacia. And the epithelium within the eye is usually columnar. So usually what ends up happening is we're actually losing the you're losing the epithelial integrity within the eye. So we have this columnar epithelium with these tight junctions, and that's to protect any bacterial infections within the eye. And as our cells lose the columnar and become squamous, now we have made it more leaky, and bacteria are able to go within the cells, and basically we end up first having a bunch of conjunctivitis, and you will see the eyes, usually you have a lot of eye infections and conjunctivitis pus all throughout the eye, and all those bacterial infections and the scar tissue. So the cornea first becomes hard because of the scar tissue that's forming, because we are cleaning up all these this onslaught of bacterial infections. And then after a while, it just becomes soft. And because this is actually not night blindness, and it has really nothing, exophthalmia really has nothing to do with how the eye and the retinol is being activated. It's all due to the epithelial integrity and having significant bacterial infections, chronic bacterial infections within the eye. This ends up being the most common cause of blindness in young children, and it is irreversible. So once an individual or a child gets exophthalmia, they are blind for life. They can't, unless you do a eye transplant, they are never going to have vision again. Another deficiency symptom is hyperkeratinization of the skin. So when we have, just like when we have low levels of vitamin A, our columnar cells are going to become squamous, and we're going to end up having our vitamin A is controlling cell growth. So if we don't have adequate vitamin A, we're going to have overgrowth of our skin cells, and so it's hyperkeratinization. So it looks like a severe case of goosebumps all the time. Here we also have squamous metaplasia, which is another hyperkeratinization of our columnar epithelium. This is not going to be clinical. Usually you'll see squamous metaplasia if you do histology. So you take a biopsy of intestinal cells, and then you can see the squamous metaplasia form. In addition, as I mentioned before, you get increased morbidity and mortality to common diseases, especially in developing countries. Measles is chronic and plaguing many countries, so you have a lot of increased mortality in these young children due to measles. So here's a map of all the world and where we have the most common deficiency, and vitamin A is by far has the most deficiencies throughout the world. We don't think of it here in the U.S. because you could see we have very mild vitamin A deficiency. Very rarely are we going to see any vitamin A deficiency in individuals. If they do, it's going to be more due to a fat malabsorption concern. Similarly, Europe, not a concern. Russia and Australia, we're not worried. We have some components in South America and in Mexico. Africa is plagued with vitamin A deficiency. Same with India and Southeast Asia. We can see a significant amount of vitamin A deficiency that's occurring. So one of the main reasons why is vitamin A is primarily found in its most readily available form in animal protein. So it's a lot obviously in liver because that's where it's stored. You can find it in muscle tissue and eggs and milk. So more of our developed affluent countries where people have adequate ability, have the funds to where they can consume those particular ingredients, we don't have any issues. However, the vast majority of the developing world, those that are poor, they do not have access to the expensive animal proteins that have high levels of vitamin A. In addition, the majority of these areas, one of the main things they're consuming is rice. So we'll have rice and beans, for instance, and rice has essentially very low vitamin A. There's not very many carotenoids, provitamin A carotenoids at all. And they also are not consuming any, their legumes that they're consuming don't have any provitamin A carotenoids either. So many people plagued with vitamin A deficiency. And because of this is why the WHO, the World Health Organization, actually recommends young infants, as soon as they're born, they get a bolus dose of 50,000 international units of vitamin A, and that's to hopefully boost their stores and improve the infant mortality and prevent them from getting exothermia. So here on the right-hand side, we have a picture of the exothermia. You could see the eye here is, this is a Jordanian infant. So the cornea is very soft, and this infant has lost their vision for the rest of their life because once we have exothermia, it cannot be, it's not reversible. In addition, we have the hyperkeratinization, and you can see all throughout this child's stomach, it looks like they have a severe case of goosebumps. And it is not due to goosebumps at all. It is the hyperkeratinization of the skin. Ruminants can also get vitamin A deficiency, so they can meet the requirements with our carotenoids, and they're able to convert about 20 to 30%. But remember that vitamin A deficiency is the least stable. So if you have the hay or whatnot drying out on the field, you're going to decrease the amount of vitamin A with every passing day because it's going to be denatured by the UVA and UVB rays, in addition to the temperatures that it's subjected to. So ruminants, grass-fed, pasture-raised ruminants are susceptible to vitamin A deficiency. So here we have a calf, and you can see a lot of tearing. So we have the lacrimation or tearing. And why is this calf tearing? Well, it's because it is fighting bacterial infections within the eye. So that is your eye's main defense and fighting bacterial infections. You ever notice you get anything, a bug fly into your eye, instantly your eye gets all watery, and that's its way of protecting the eye and trying to get rid of whatever infections may be in there. Our tears have a lot of antibacterial proteins within them. So that's why you have increase in the tearing, and that's all due to increased bacterial infections. Other symptoms that you'll see is you'll have reduced feed intake and growth, rough hair, and that's all because we have this change in our keratin proteins. So we're increasing the expression of some of our keratin proteins, and we're decreasing the expression of some of the other ones. So that's going to result in rough hair. We'll also get night blindness, and we will have significant amount of reproductive problems, many abortions, reabsorbed fetuses, etc. Now, our poultry also can be subjected to vitamin A deficiency. They can meet all their requirements with carotenoids. Their conversion is almost 100%, which is not the case for humans, and obviously not the case for ruminants. So they can meet it all with our carotenoids. However, if they do become subjected to vitamin A deficiency, we have various symptoms, including conjunctivitis. So this is an infection of the eye. You'll have squamous metaplasia. As I mentioned, this is more of this isn't so much clinical. It is going to be more of a histological histological analysis. So you have to do some pathology to determine the squamous metaplasia. We have lower disease resistance, so they are going to be more susceptible to various diseases. You'll see a lot more E. coli and salmonella infections within these birds. In addition, we're going to have a lack of muscle coordination. So here in this top picture, we have some chicks that were made vitamin A deficient, and they are unable to walk correctly. And I can attest to this for my doctorate degree. I looked at vitamin A deficiency in chickens, and once the vitamin A deficiency hits, they really have a hard time standing and walking. Here you can see some turkeys. We have some 6-week-old turkeys. This one on the left was provided a vitamin A deficient diet, and you can see the stunted growth. It is sitting down because it does not feel well, so it doesn't want to be standing up, but it does have stunted growth. Here is a version of chickens, so we have the lack of muscle coordination. They don't want to stand. And these two chickens on the left and the right, where the one in the middle had ample amounts of vitamin A, so it is willing to stand and be happy. And you'll also maybe hard to tell, but we have ruffled feathers, so the chickens are not happy. They don't feel well if they don't have adequate levels of vitamin A. Here we have a picture of a turtle. Turtles can get vitamin A deficiency also. So this one actually has conjunctivitis within the eye. You could see how pussy the eye is within this turtle. It's unable to open it, and that's mainly because it's all crusted shut because of all the pus within the eye. So as I said, we get secondary bacterial infections because we have the squamous metaplasia occurring within the epithelium of the eye. And those secondary bacterial infections are what's going to end up causing the exothermia within this turtle. So vitamin A is one of the trickiest of all the vitamins, because you would say, well, if it's the least stable of all the vitamins, we'll just put more in, and then by the time the animal consumes the food or takes this multivitamin, then it'll have ample amounts and it'll just be just fine. Difficult thing with that is it is the most toxic. So we have the lowest or the narrowest range that we can feed our vitamin A. So these levels are for humans, so this is micrograms of retinoid equivalents per day. So this is taking into account carotenoids that can be converted to retinoids. So If we have between 0 and 50 micrograms of retinoic acid equivalents, we're going to be in a deficient state. So this is where we'll have night blindness, exothermia, etc. Our normal, where it's going to be between 500 and 15,000. So you can see this is still pretty decent wide range. And then if you consume greater than 15,000, that's where you're going to get into the toxic levels. And I do want to state that it is very unlikely that you will have any toxicity if you are utilizing carotenoids, because your body is able to better control the level once it has adequately converted your carotenoids over to vitamin A. You're not going to keep on converting your carotenoids, your beta carotene, over to retinol once you have adequate amounts. So that's where, if you love carrots, you just eat them all the time. Why you may end up having orange skin is because your body is then taking all that beta carotene and putting it into the fat of your skin cells instead. So how does vitamin A cause toxicity? So this actually occurs when our binding proteins are saturated and we end up having free vitamin A, damaging the cells. So with this, we'll get skeletal malformations. You can get internal hemorrhaging and slow growth. And internal hemorrhaging is actually thought because the high levels of vitamin A may actually be inhibiting the activity of your vitamin K. So that's where that internal hemorrhaging is occurring. We're also going to get slow growth, and you're going to have reduced liver and kidney function. So your liver is going to have all those vitamin A stored in the stellate cells, and so we may be making more of those stellate cells. We're also trying to get rid of all the excess vitamin A through our kidneys. So that's where we're going to have effects on our liver and kidneys. We're also going to have significant birth defects because our vitamin A is controlling cell growth. If our fetus is exposed to too much, we're going to have many deformities occur. It's very rare to have vitamin A toxicity. Naturally, you're never going to see it. Usually, it's going to occur in people by consuming too many supplements or over-consuming liver. So if you just love liver, then you just eat it morning, noon, and night, then you're maybe at risk of being toxic for vitamin A. As I mentioned, beta carotene cannot cause toxicity, and that's because of the negative mechanism in place. So you're never going to have that occur. So if you're ever concerned, then how much vitamin A you're consuming, just eat more carrots, less chicken livers, and you'll be fine. You just may be a little orange. So the levels of vitamin A that are going to cause toxicity, so in humans, anything greater than 100,000 international unit per day for weeks to months on end, you're going to become toxic. Ruminants, 100 times the daily requirement for weeks. The daily requirement is 66,000 IU per kilogram of the diet. Cats, for instance, they consume 20,000 to 40,000 micrograms per kilogram of their body weight for greater than 2 years. So that's a long time. Then you are possibly going to get into toxic levels and see some clinical toxicity signs. So what are some of the foods that are going to have a lot of vitamin A? So here you could see our beef liver has the highest amount of vitamin A, so 10,000 retinoid equivalents. compared with, and we're using this because we have many of our other carotenoids coming from our vegetables. Pumpkin has a lot of carotenoids, sweet potato, carrots, spinach. And here you can see our eggs and our whole milk. They do have some vitamin A, but it's not going to be significant amounts. So if you're really concerned, having a little bit of animal liver will increase your vitamin A levels.